Hi, good morning. Today we are going to start our next session, section 5.2, Fredholm theory of compact operators. So, just recall what you mean by a compact operators. Okay, just I am recalling all these things. Just to recall. Now, what do you mean by a compact operator? A linear operator A from x to y is a compact operator if and only if every bounded sequence xn belongs to x, the sequence axn has a Cauchy subsequence. Clear? Compact operator means every bounded sequence must have a Cauchy subsequence. Now there is another result like compact set. Also we need a pre-compact set. Definition of a pre-compact set. Now what do you mean by a pre-compact set? K is a pre-compact set if every sequence xn belongs to K has a Cauchy subsequence xni. Every sequence xn belongs to K has a Cauchy subsequence xni. Then we call K is a pre-compact set. Clear? Now we will look at one if and only if condition for an operator A to be compact. An operator A from x to y is compact if and only if the image of a unit ball of x is a pre-compact set in y. Okay, you must remember these. Image of a unit ball. What is unit ball? Unit ball of x is set of all x such that norm of x equal to 1. Image of a unit ball means set of a of d of x. That is, which is equal to set of all ax such that norm of x equal to 1. This must be a pre-compact set in y. Okay, just recall all these things. Now we are starting our session. In this section, we are discussing one lemma. Let E1 be a closed subspace of E such that E not equal to E1. That means E1 is a proper subspace of E and E is a subspace of X. Then there exists, the result says there exists a y naught belongs to E with norm of y naught equal to 1 and such that the distance of y naught to E1 satisfies the condition distance of y naught and E1 is greater than or equal to 1 by 2. This lemma is very important. You must with the clear uh, all the terms, okay, and listen carefully. We have a lot of things in today's section, so listen carefully each term. Let E1 be a closed subspace of E, okay, and E1 is subset of subspace of E, subspace of X. Then we have to prove there exists a Y naught belongs to E with satisfies this condition with the norm of Y naught equal to 1 and such that distance between Y naught and E1 is must be at least 1 by 2. This is what we have to prove. Okay, so if you look at like this, suppose this is our E and this is E1, okay, and you have to prove there exists some Y naught. Y naught belongs to E, Y naught may be here, okay, Y naught. Y naught, we can't take Y naught here because distance between Y naught and E1 must be greater than or equal to 1. So the lemma says that there exists a Y naught belongs to E with the norm of Y naught equal to 1 and the distance between Y naught and X must be greater than or equal to 1 by 2. Okay. So, given y1, E1 is a subspace of E, therefore E1 not equal to E. That means clearly the complement E minus E1 is non-empty. Okay. Choose y belongs to E minus E1. Okay. such that distance between y and e1 equal to a, which is greater than 0. Is it this possible to choose such a y? That is our first problem. Okay, we have to choose y belongs to this one such that distance between y and e1 is equal to a greater than 0. What is e1? E1 is a closed subspace. E1 is a closed subspace of E. So what about E1 complement? E1 complement is open. So we are choosing some point y here. E1 complement is open means you can find a neighborhood of y completely contained in E1 complement. Okay. So this ball is here and this consists of all the points in E1. Therefore clearly the distance between y and E1 is y and E1 is clearly greater than a. Such a y exists since E1 is closed. This is enough and just okay, you remember this. There is no need to write these things for exam. E1 complement is open. Choose a point y in this one. Then clearly there exists a ball with the center y and completely contained in E1 complement. Therefore distance between y and E1 is equal to a. That means clearly greater than 0. Now choose x naught belongs to E1 such that norm of y minus x naught is less than 2a. Okay, so distance between y and E1 is greater than a. This must be at least a. This is equal to, sorry, this is equal to okay, this is equal to a and which is greater than 0. Okay, so choose some x naught belongs to E1 such that norm of y minus x naught is less than 2a. We are choosing some x naught belongs to E1 such that norm of y minus x naught is less than 2a. By our definition, distance between y and E1 is equal to a. Okay, we can choose like this and you choose some x naught. This must be at least a. Choose some x naught belongs to E1 such that norm of y minus x naught is strictly less than 2a. Now then choose y naught as y minus x naught divided by norm of y minus x naught. Okay. Then what is norm of y naught? Norm of y naught is norm of y naught is norm of y naught is 1. Okay, norm of this one. Now norm of y naught is equal to norm of this. Okay. So if you choose some x naught belongs to E1 with this condition, then we get norm of x naught is equal to 1. Therefore, for any x belongs to E1, therefore for any x belongs to E1, norm of y naught minus x equal to norm of this one, and multiplying this with norm of y minus x naught minus x into y minus x naught divided by norm of y minus x naught. Now what about x naught? X naught belongs to E1. Okay. So what about the remaining terms? These terms x naught, this you can write as y minus x naught plus like this. Now what about this term? X belongs to E1. E1 is a subspace scalar multiple of this term is again in E1 and also x naught. We choose x naught also belongs to E1. Therefore, this term completely contained in E1. So what about distance between y and a point in E1? Distance between y and e1 is, so distance between, okay, y and e1 is equal to a. Okay, that means norm of norm of y minus x naught plus x, norm of y minus x naught is equal to, is actually greater than or equal to a, because distance is infimum. Okay, so what about norm of y minus x naught? This is less than or equal to 2a. Therefore 1 by norm of y minus x naught is greater than or equal to 1 by 2a. So this divided by y minus x naught is greater than or equal to a by 2a, which is equal to 1 by 2. Therefore y naught minus x is greater than or equal to 1 by 2 for any x belongs to E1. Norm of y minus x naught is greater than or equal to 1 by 2 uh, for any x belongs to E1. This implies distance between y naught and E1 is greater than or equal to 1 by 2. Hence the lemma. Okay, must clear all these things. Okay, now there is another lemma, sorry, corollary. If dimension of x equal to infinity, then the identity operator I from x to x is not compact. What is the meaning of that? If x is an infinite dimensional, if x is an infinite dimensional space, then the identity operator cannot be compact. So, for proving compactness, we have to prove actually image of a unit ball of x is a precompact set in Y. Okay, so to prove it is not compact, it is enough to prove that image of a unit ball of x is not a precompact set in Y. Here, image set is also x, therefore it is enough to prove that image of a unit ball of x is not a precompact set in Y in X. So to prove I from x to x is not compact, it is enough to prove that the image of a unit ball is not precompact. As it is an identity operator, what about the image of an identity operator? Image of a unit ball. That is again a unit ball. So we have to prove image of a unit ball is not precompact. Clear? So for this, what we have to prove? Again, move to the definition of precompact. So what is the precompact definition? Every sequence in Xn has a Cauchy subsequence. So to prove it is not precompact, we have to arrive a result that there exists a sequence that it does not have a Cauchy subsequence. Clear? So consider a family of subspaces E1 proper subspace of E2, subspace of E3, etc. En subspace, etc. Where dimension of En equal to n. Consider this family of subspaces. Does there exist such a subspace? For this, we have given X is an infinite dimensional space. Therefore, you choose some x1 and not equal to 0 and e1 equal to span of x1. Then what about dimension of e1? 1. Okay. Now is span of x1 equal to our x? No, because x is infinite dimensional. So you choose some x2 not belongs to span of x1. Okay. Such that therefore x2 not belongs to e1 and set e2 equal to span of x1 x2. In this case, dimension of E2 is equal to 2 and clearly E1 is a proper subspace of E2. Continuing like this, we will get this. Okay. So consider a family of subspaces E1, E2, etc. En. And given that each EI is a finite dimensional and we know that finite dimensional subspaces are closed. Therefore, EI is a closed subspace of X for every I. And applying above lemma, we get there exists a yi belongs to ei with norm of yi equal to 1 such that distance between yi and ei minus 1 greater than or equal to 1 by 2. For example, if you consider E1 and E2, E1 is a closed subspace of E2. There is no need to write all these things in your exam. You can write this in your notebook. Okay. E1 is a closed subspace of E2. Therefore, there exists a Y naught. By previous theorem, there exists a Y naught belongs to E2 with the norm of Y naught equal to 1 and a distance between Y naught and E1 greater than or equal to 1 by 2. Okay. And we are denoting this Y naught as Y2. So, where is Y naught? Y naught is actually in E2 minus E1. Therefore, here Y2 is in E2 minus E1. Similarly, if you consider E2 and E3, there exists a Y naught belongs to E3 such that norm of Y naught equal to 1 and a distance between Y naught and E2 greater than or equal to 1 by 2. And we denote this Y naught as Y3. So Y3 is in E3 minus E2. Because in our theorem, here in the proof, here we choose Y belongs to E minus E1. Okay, E1 is contained in E and Y we choose Y belongs to E minus E1. And our Y naught is okay. So distance between Y3 and E2 is greater than or equal to 1 by 2. But our Y2 belongs to E2. Okay. So norm of Y3 minus Y2 must be greater than or equal to 1 by 2. Proceeding like this, we get for any I not equal to j, norm of Ya minus Yj is greater than or equal to 1 by 2. That means Ya is not a Cauchy sequence. Okay. So norm of Ya equal to 1 for every I means this sequence Ya is a sequence in D of x, but it cannot have a Cauchy subsequence. Therefore, there is no Cauchy subsequence for this is not a Cauchy subsequence. Therefore, there is no Cauchy subsequence for this sequence. This implies D of x is not a pre-compact set. Therefore, I from x to x is not a compact operator. You must remember this definition. Sorry, statement of the corollary. If x is an infinite dimensional space, then the identity operator cannot be a compact operator. Moving to next proposition. Before that, we have to remember all these things. We are assuming this from the rest of the session. Okay. In the from now onwards, we are assuming every x is an infinite dimensional Banach space. And whenever we mention T, that T must be a compact operator. Okay, whenever we mention T, the T must be a compact operator. And we denote T lambda for the operator T minus lambda I. This notation is used for T minus lambda I. And we denote delta lambda as image of T lambda. Image of T lambda. Okay. Delta lambda is image of T. That means this is actually image of T minus lambda I. This is actually image of T lambda is T minus lambda I. Also, we are using our above lemma frequently. Okay. So now we are going to prove one proposition. Proposition 5.2.3. For every compact operator T, 0 belongs to sigma of T. That means 0 is a spectrum value. Spectral value. Okay. Or 0 is a spectrum point. So we are assuming the contradiction. Suppose 0 not belongs to sigma t. That means sigma belongs to rho of t. That means sigma is a is in resolvency. Okay. So what is the meaning of that? Lambda is not a spectrum point means t minus lambda I whole inverse is a bounded operator. Here T minus lambda I means lambda is 0 I. That means T inverse is a bounded operator. Okay. So T inverse is a bounded operator and T inverse T equal to I. And just to recall our proposition 4.3.4, that K is a compact operator, then K is an ideal in L of X, Y, L of X. That means is an ideal means here if you consider this, if A is a compact operator and C is in LYZ, here we are using LXX. Okay, so uh, CA must be a compact operator. CA must be in KXXL. If you replace here, if you consider this, CA must be in KX. Okay, so here T is a compact operator and CT is a compact operator. By as it is an idea, CT must be a compact operator for any C belongs to LXS or LX. Okay, so we are considering T inverse because L, what is LXX? LX, or you can write this as L of X. What is L of X? Such a bounded operator. CT must be a bounded operator by our proposition, this proposition. So C, if you take C as C is any bounded operator, and CX must be, sorry, CT must be in KX, sorry, KX. That must be a compact operator. Here, if you take C as T inverse is a bounded operator and T inverse T must be a compact operator by our assumption. Okay, so I must be a compact operator because T inverse T equal to I must be a compact, which is a contradiction. This contradiction arises as we take 0 belongs to 0 not belongs to sigma T. That means 0 belongs to rho T. Therefore, 0 must belongs to sigma of T. Clear? Now moving to our last proposition. For every epsilon greater than 0, there is only a finite number of linearly independent eigenvectors corresponding to the eigenvalue lambda I with mod lambda I greater than or equal to epsilon. Once again, for every epsilon greater than 0, there is only a finite number of linearly independent vectors corresponding to the eigenvalue lambda I with mod lambda I greater than or equal to epsilon. That means if you consider an epsilon ball here, then the result says that there is only a finite number of linearly independent eigenvectors corresponding to the eigenvalue lambda I with mod lambda I greater than or equal to epsilon. That means eigenvectors corresponding to mod lambda I greater than epsilon. Okay, and that is mod lambda I greater than epsilon are only in finite number. Okay, this there exists only finite number of sigma I belongs to sigma p, sorry, lambda I belongs to sigma p such that mod lambda is greater than or equal to epsilon, and for every lambda I has a finite multiplicity, that is dimension of kernel of t lambda I is less than infinity, and we are in general we are saying dimension of kernel t lambda is less than infinity. What is the multiplicity of lambda I? Multiplicity of lambda is the dimension of kernel of, what is multiplicity of lambda I? Is same as dimension of kernel of t minus lambda I. This is the multiplicity of lambda I. Okay, and this is dimension of kernel of t lambda I. Okay, so we are assuming, suppose there exists infinite number of linearly independent vectors such that txi equal to lambda ix. That means lambda is a eigenvalues with satisfies this condition. That means mod lambda is greater than or equal to epsilon. Okay. The theorem says that there exists only finite number of eigenvectors corresponding to the eigenvalue lambda I with lambda I lambda I belongs to this part. Okay, so we are assuming the contradiction there exists infinite number of linearly independent vectors, and we will arrive at a contradiction. So yes, this is an infinite dimensional space. We can consider as in the previous case, ek equal to span of x1, x2, etc. xk. Then clearly ek is a subspace of ek plus 1. Since each k is finite dimensional, it is closed by lemma 5.2.1. The exists a yk belongs to ek with the norm of yk equal to 1 and a distance between yk and ek minus 1 greater than or equal to 1 by 2. Okay, we have this result already. Now consider the sequence T of, using this yk, we are constructing another sequence T of yk by lambda k. Okay, yk is in x, so for T of yk is in tx. Therefore, consider the sequence T of yk by lambda k in tx. So yk belongs to ek and yk equal to a1 x1 plus a2 x2 plus etc. plus ak xk. Therefore, that is yk equal to sigma I where, because yk is in span of x1, x2, etc. xk. Therefore, yk you can write like this. Okay, and in summation notation we can write like this. Now, what is T of yk by lambda k? And T is linear. Therefore, we can write this as 1 by k T of yk and apply T here 1 by lambda k. Sigma I varies from 1 to k. T of ai xi and 1 by lambda k sigma I varies from 1 to k ai T of xi and 1 by lambda k sigma I varies from 1 to k ai txi is same as lambda I xi. Txi is same as lambda I xi. Okay, and this is equal to, you can take lambda k inside because this lambda k is a constant. Sigma I varies from 1 to k ai by lambda I by lambda k xi. And whenever k, this I become k, this become lambda k by lambda k, and this term is 1. And here this become ak and xk. So we are choosing the last term first, then write the remaining term. So ak xk plus sigma I varies from 1 to k minus 1 ai lambda I by lambda k xi. Now we are adding ak xk, sigma I varies from 1 to k minus 1 ai xi and subtracting this term. And summing these terms, sigma I varies from 1 to k ai xi plus this sum. This is ai lambda I by lambda k, and here we have a minus sign here. Therefore, this become minus 1 lambda I by lambda k minus 1 xi. Okay. Here actually each term is, if you consider this term is actually a1 x1 plus a2 x2 plus etc. And this term is a1 x1 lambda 1 by lambda k plus a2 x2 lambda 2 by lambda k, like this. So you are combining these two terms, a1 x1 lambda 1 by lambda k minus 1. Here this is minus sign. Okay, similarly a2 x2 lambda 2 by lambda k minus 1. So in general this become like this. Okay, so this is actually yk plus this one, and this is actually yk plus zk, and zk is this one, and clearly this is in ek minus 1. Okay, because this is the linear combination of x1 x2 etc xk minus 1, and which is equal to ek minus 1. So T of yk by lambda k equal to yk plus zk, where zk belongs to ek minus 1. Suppose k greater than 1. That means k greater than or equal to n plus 1, that is En plus 1 is contained in Ek. In general, you can say En is contained in Ek minus 1. So what about mod T of Yk minus mod T of Yn? Mod T of Yk by lambda k minus mod T of, sorry, norm of T of Yk by lambda k minus T of Yn by lambda n. We can write like this, we can write like this. We can write yk minus this term. Now if you look at yn, where is yn? Yn belongs to En. En is contained in ek minus 1. Where is zk? Zk belongs to ek. Ek is contained. Ek minus 1 is contained in Ek. Okay. Where is our Zn? Zn belongs to En. So finally what we get? We get norm of Yk minus an element in Ek minus 1. Okay. But we know that distance between yn and here we have distance between yk and ek minus 1 is greater than or equal to 1 by 2. Therefore, distance between yk and an element in ek minus 1, this must be clearly greater than or equal to 1 by 2. Okay. Okay, so this sequence T of yn by lambda n cannot have a Cauchy subsequent because T of this difference norm of T yk by lambda k minus T of yn by lambda n greater than or equal to 1 by 2 whenever k is greater than n. Okay. Therefore, this sequence cannot have a Cauchy subsequence. Since norm of EI since mod lambda I greater than or equal to epsilon, 1 by mod lambda is less than or equal to 1 by epsilon. Norm of yn by lambda n is less than or equal to 1 by epsilon. Why? Norm of yn is 1. Therefore, yn by lambda n is a bounded sequence, but its image sequence cannot have a Cauchy subsequence. This is a contradiction to our compactness of T. Okay. By compactness, given any bounded sequence, there exists a Cauchy subsequence. Therefore, there is only a finite. This contradiction arises just because our we have assumed a sigma set x1, x2, etc. That sequences there exists an infinite number of linearly independent vectors. Therefore, for every epsilon greater than 0, there is only a finite number of linearly independent eigenvectors corresponding to the eigenvalue lambda I with mod lambda I greater than or equal to epsilon. Okay. And therefore, in the point spectrum, sigma t of a compact operator T on a infinite dimensional Banach space X, at most a sequence lambda I converging to 0 and every lambda I have a finite multiplicity, because after that if mod lambda I greater than epsilon, this part consists only a finite number of eigenvectors. Okay. All other eigenvectors must be in this range. Okay. That means that sequence converges to 0. Okay. That's all for today's class.